Hey YouTube, what's up? Dr. T here, and welcome to the Altcoin Express and my hometown, St. Petersburg, Florida.
Say you want to predict some output value y given some input value x. For example, maybe you want to predict your score on a test based on how many hours you sleep and how many hours you study the night before. To use a machine learning approach, we first need some data. Let's say for the last 3 tests, you recorded your number of hours studying, your number of hours sleeping, and your score on the test. We'll use the programming language Python to store our data in 2-dimensional NumPy arrays. Now that we have some data, we're going to use it to train a model to predict how well you will do on your next test based on how many hours you sleep and how many hours you study. This is called a supervised-regression problem. It's supervised because our examples have inputs and outputs. It's a regression problem because we're predicting your test score, which is the continuous output. If we were predicting your letter grade, this would be called a classification problem and not a regression problem. There are an overwhelming number of models within machine learning. Here, we're going to use a particularly interesting one called an artificial neural network. These guys are loosely based on how the neurons in your brain work and have been particularly successful recently at solving really big, really hard problems. Before we throw our data into the model, we need to account for the differences in the units of our data. Both of our inputs are in hours, but our output is a test score scaled between 0 and 100. Neural networks are smart, but not smart enough to guess the units of our data. It's kind of like asking our model to compare apples to oranges, where most learning models really only want to compare apples to apples. The solution is to scale our data. This way our model only sees standardized units. Here, we're going to take advantage of the fact that all our data is positive and simply divide by the maximum value for each variable, effectively scaling our result between 0 and 1. Now we can build our neural net. We know our network must have 2 inputs and 1 output because these are the dimensions of our data. We'll call our output layer y hat because it's an estimate of y, but not the same as y. Any layer between our input and output layer is called a hidden layer. Recently, researchers have built networks with many hidden layers. These are known as deep belief networks, giving rise to the term deep learning. Here we're going to use 1 hidden layer with 3 hidden units. But if we wanted to build a deep neural network, we would just stack a bunch of these layers together. In neural net visuals, circles represent neurons and lines represent synapses. Synapses have a really simple job. They take a value from their input, multiply it by a specific weight, and output the result. Neurons are a little more complicated. Their job is to add together the outputs from all their synapses and apply an activation function. Certain activation functions allow neural nets to model complex, nonlinear patterns that simpler models may miss. For our neural net, we'll use sigmoid activation functions. Next, we'll build out our neural net in Python. Last time, we set up our neural network on paper. This time, we'll implement it in the programming language Python. We'll build our network as a Python class, and our init method will take care of instantiating important constants and variables. We'll make these values accessible to the whole class by placing a self dot in front of each variable name. Our network has 2 inputs, 3 hidden units, and 1 output. These are examples of hyperparameters. Hyperparameters are constants that establish the structure and behavior of our network, but are not updated as we train the network. Our learning algorithm is not capable of, for example, deciding that it needs another hidden unit. This is something that we must decide on before training. What neural networks do learn are the parameters, specifically the weights on the synapses. We'll take care of moving our data through our network in a method called forward. Rather than pass inputs through the network one at a time, we're going to use matrices to pass through multiple inputs at once. Doing this allows for big computational speedups, especially when using tools like MATLAB or NumPy. Our input data matrix X is of dimension 3 by 2 because we have 3 2-dimensional examples. Our corresponding output data, y, is of dimension 3 by 1. Each input value, or element in matrix X, needs to be multiplied by a corresponding weight and then added together with all the other results for each neuron. This is a complicated operation, but if we take the 3 outputs we're looking for as a single row of a matrix, and place all our individual weights into a matrix of weights, we can create the exact behavior we need by multiplying our input data matrix by our weight matrix. Using matrix multiplication allows us to pass multiple inputs through at once by simply adding rows to the matrix X. From here on out, we'll refer to these matrices as X, W1, and Z2, where Z2 is the activity of our second layer. Notice that each entry in Z is a sum of weighted inputs to each neuron. Z is of size 3 by 3, one row for each example, and one column for each hidden unit. We now have our first official formula. Z2 is equal to X times W1. Matrix notation is really nice here because it allows us to express the complex underlying process in a single line. Now that we have the activities of our second layer, Z2, we need to apply the activation function. We'll independently apply the function to each entry in matrix Z using a Python method for this called sigmoid, because we're using a sigmoid as our activation function. Using NumPy is really nice here because we can pass in a scalar, vector, or matrix. NumPy will apply the activation function element-wise and return a result of the same dimension as it was given. We now have our second formula for forward propagation. Using f to denote our activation function, we can write that A2, our second layer activity, is equal to f of Z2. A2 will be a matrix the same size as Z2, in this case 3 by 3. To finish forward propagation, we need to propagate A2 all the way to our output y hat. We've already done the heavy lifting in our previous layer, so all we have to do now is multiply A2 by our second layer weights W2 and apply one more activation function. W2 is of size 3 by 1, one weight for each synapse. Multiplying A2, a 3 by 3, by W2, a 3 by 1, results in a 3 by 1 matrix Z3, the activity of our third layer. Z3 has 3 activity values, one for each example. Last but not least, we'll apply our activation function to Z3, yielding our official estimate of your test score, y hat. We need to implement our forward propagation formulas in Python. First, we'll initialize our weight matrices within our init method. For starting values, we'll use random numbers. We'll implement forward propagation in our forward method, using NumPy's built-in dot method for matrix multiplication and our own sigmoid method. And there you have it, a Python class capable of estimating your test score given how many hours you sleep and how many hours you study. We can pass in our own input data and get real outputs. Now, you may be noticing that our estimates are quite terrible. That's because we have not yet trained our network, and that's what we're going to work on next time. Last time, we set up our neural network on paper. This time, we'll implement.
So using this series, I started off and belabored for quite a while. I tried to kind of use house prices from Zillow and area of the property, something like that. So we have input decimal, we have NumPy, matplotlib, and the style. This was the data I used, and that presents the data from matplotlib. These were the normalized values of the data. You can forget this, it comes later on. We've got our class, the init levels. This is where we get our weights, and they go into the forward pass down to here, and then we'll pop down a little bit further, because this is all the class is teaching you so far. And there's the sigmoid value that goes in, which gets picked up later on. And I'll go through the rest of the talk and pop up my various bits of code. Later on, I couldn't follow what he was doing, so I had to just work out my own thing and see how it goes. And then there were many iterations down the line, and the linearity data didn't come out well because there's only one layer there, but the whole point of this is to be able to kind of code one hidden layer of an artificial neural network.